Travel first.
I'm Taylor Mango. I'm also civil fourth year, and I'm also specialized in hydro, and I hope to get a job in hydro. But you know, maybe I'll get a job in transportation and not look back. Who knows? But yeah, that's me.
Hi, I'm Monica Tiff. I'm also fourth year civil, specializing in water resources. I'm really interested in wastewater treatment in general, including like biogas treatment or even desalination. But I do currently work in the flood levees and checks department, so that is what I'm doing right now.
Hi, I'm Matt Bravely. I'm also fourth year civil engineering water, gonna be most of us. I'm currently interested in more of the urban development and the utility design aspect. That's currently what I do now for work. I carry that on out of school, but that sort of aspect of the water, sewer, snorkeling kind of interests me.
Hello everybody, my name is Justino and I'm a fourth year civil engineer at UC Irvine. My main interest is, I'm specializing in water resources and hydrology, which my interest is mostly focused on civil engineering as a whole. Like, I really like how like storm water runoff and where I live is like Coachella Valley, and overall whether like there's a huge arsenic problem. So for me overall I wanna like provide that infrastructure and basically improve upon the infrastructure where it's needed, and that's what basically drives me to be a civil engineer.
Hello, my name is Corey. I'm a fourth year civil engineering major, specializing in general. I'm a general faculty. I'm interested in volunteering and public services aspects of water resources engineering, and that's where I hope to work in the future of my career.
Sure.
Well, first off, thank you guys for being here. We're really excited to be here and be able to show you the work that we've been doing for the past 4 months or so. We started this project at the beginning of January, so again, a lot of hard work, time spent meetings almost every week. So really excited to just be here and present this to you guys. So this is our senior design project. It's the OASIS DPR facility. So here's our overview of the project. Maybe you know some of this information, but I'll go ahead and recap some of it. So essentially it's a DPR facility, meaning it's direct potable reuse. So that water that's being treated in the tertiary wastewater treatment facility is being pumped directly into potable drinking water lines. So it's taking secondary effluent from the existing facility in Moulton Niguel, and it's going to produce about 3 million gallons per day. This is different than indirect potable reuse, which is water that gets injected to groundwater basins. So the fact that it's DPR instead of indirect potable reuse, it's pretty monumental because this water is water that's scarce. Where in California, water is definitely a resource that we need to value pretty highly because we're in a drought. So the fact that we can take this water and directly put it back in the drinking water lines, and conserve water as best we can, it's pretty important. And I think getting this message out here to the public and showing everyone that we can treat water and bring that to the public as fast as we can in the most efficient way is really important. So I'll pass it off to Mark to talk about DPR requirements.
Thank you, Josh. Well, overall for the DPR regulation, we have 5 types of main requirements. And these are the one to have access the advanced treatment system, have a proper safety and monitoring process, as well as having a source control and pre-treatment system, and have a proper operation requirements, and as well as to keep the public standards and safety to ensure the quality of water. And overall, The three types of advanced treatment system consists of microfiltration. Three types that are required for the DPR process are the microfiltration, reverse osmosis, and the advanced oxidation. Overall, the final disinfection product is not basically required, but it's recommended to have it to ensure the safety and overall the cleanliness of the water to be secure. Overall, the monitoring process and the safety protocols, it mostly consists of making sure that the runoff is overall the runoff to be the right amount of flow, make sure the pressure doesn't overflow and overheat, as well as the total amount of carbon, make sure that not enough amount of bacteria is in there, and it's important to have an automatic shutdown and overall runoff so it doesn't interfere or infect the other sites of the pre-treatment. It's important to have a source control, and it's needed to have a proper sample, and it's important to sample those wastewater treatment and making sure that the log reductions are 10 or more to secure that all viruses and bacteria are destroyed and operational. In order to the DPR to be operational, it needs to be reliable, needs to have enough amount backups, and have proper operational training in order to be operational with the right amount of reports ranging from days, weeks, months, and even annually at times. It's important, very important that the DPR presents itself through the compliance and standards, through itself, through regulations, as well as for the public awareness and safety, and to acknowledge the potential risks within the community. Now I'll pass it on to Tyler to discuss more about this.
Okay, so let's talk about the treatment train selection process. We had 3 different alternatives we were selecting from that you can see the picture there. And we had 3 different selection criteria we were considering, including pathogen control, chemical control, and other specific DPR regulations that were outlined for us. For the pathogen control, there's a certain amount of removal of virus, Giardia, and Cryptosporidium that needs to occur 90% of the time, and a slightly lower level that needs to be removed 100% of the time. For the chemical control, there's a lot of different stuff, but it includes an ozone and BAC process as well as an advanced oxidation process, which is UV light. And we also considered the other DPR regulations for specific units that we needed to have in that treatment train. Out of those 3, we selected alternative A, specifically because it's the train that is suggested specifically by the State Water Board DDW DPR framework, 2nd edition. By selecting this suggested train, the permitting process will be much easier and we'll go through a lot quicker. It features ozonation, biological activated carbon, membrane filtration, reverse osmosis, UV light, and free chlorine engineered storage. For the treatment processes themselves, it includes ozonation, which injects ozone into the flow, breaking down organic pollutants, and then later decomposing back into oxygen. Biological activated carbon is both a physical barrier and a wall of microbial growth that can break down organic pollutants, while the carbon itself absorbs residual contaminants. The membrane filtration is a semi-permeable membrane with tiny little holes in it that removes suspended solids, bacteria, viruses, and some other dissolved contaminants as well. Reverse osmosis is another semi-permeable membrane that removes contaminants, including salts and other impurities. UV light kills microorganisms by damaging their DNA and RNA, making them unable to reproduce. It's effective against bacteria, viruses, and protozoa.
And then finally, the free chlorine engineered storage basin. Disaffects the water by killing bacteria, viruses, and other pathogens, and leaves it stable for the next stage in its cycle. I'll hand it off to my teammate Monica.
Hi. So I created a very simplified PNID diagram, or a piping and instrumentation diagram. So I'll walk you through it with this pointer. Okay. Yeah. So I can start off with the effluent that's in the equalization tank. So that purpose of the equalization tank is basically just to stabilize the flow before entering into drain. And then attached to the tank, I've included some basic instrumentation, so it's the level gauge, and the level indicator, and our level transmitter. And then moving through the line, through the main line, indicated by the arrows, the effluent will then pump through into this injection manifold here. And then this is essentially where the ozone will be dissolved, or the ozone will enter in and dissolve with the effluent. But to backtrace a little bit, this entire contraption here is what creates the ozone. So in this little square would be the oxygen concentrator creating oxygen, or taking ambient air and creating oxygen, and then that oxygen will then flow into this ozone generator, taking the O2 and turning it into O3 or ozone. And then that will then flow through a gauge assembly and into the injection manifold, where it dissolves with the effluent going through the line. So then that water will then flow into this now ozone contact tank, which is the second process in our treatment train. And then attached up here is just a little gas vent to reduce some buildup pressure. And then attached to that is an ozone destruct unit, which is indicated by this little rectangle here. And then attached to that is called an ozone destruct water trap. And that kind of is just essentially what it sounds like. It's a ozone water trap to capture water so it doesn't damage the actual ozone destruct unit. And the purpose for this unit is just to convert that ozone back into oxygen so it doesn't get released freely into the atmosphere. But going back into the main line, the effluent will then leave the contact tank and into this UC filter right here. So the water will then permeate through this activated carbon bed, colonized by bacteria or organic compounds to kickstart a more biodegradable process of organic compounds. That's basically what the VAC filter is. And then attached to the VAC filter, I've just created this backwash system. But yeah, moving forward, the water will then flow into this feed tank. Attached to the feed tank is just a safety valve, again, for pressure buildup. But yeah, the water will then move through to this membrane module, indicating the fourth step of the treatment train, the membrane filtration. And then I've attached also some simple instrumentation there, like some pressure gauges, flow meters, and then these two variable control valves at the top just to regulate flow and also send back that concentrated waste into the feed tank. But moving down here, this is just a sample valve to take a sample of whatever's inside that feed tank without actually disrupting the entire process. So moving forward past the membrane filtration, there's also this little attached backwash system just to clean the membrane module, essentially. But moving forward, the permeate or the clean filtrate will then flow out of the membrane filtration process, and then an anti-scalar dosing will be applied. And then moving forward, it will go through this cartridge filter almost, which should be replaced every couple days or so. And then that will then move through and get pumped through into this reverse osmosis unit. It'll leave and then go into this Venturi injector. Not sure if I pronounced that right, but that's attached to this ozone destruct unit as well, since this is where the ozone will now enter into the effluent again. You can see that this line extends all the way up to the ozone generator from our initial ozone process. But yeah, that ozone will flow through these valves, needle valves, check valves, solenoid valves, and into this Venturi injector, where it dissolves in with the effluent as well to go through the process of UV AOP. So then from this injector, or we will
bit of a step back, and I focus mostly on off-site improvements for the project. So over here you can see just a basic index map of the area. Let's pretend you don't know where this is, because you obviously do. But we're on the corner of La Paz and Kings Road, Laguna Niguel. In the bottom left gray box is the regional treatment plant, which is our existing plant that we're going to pull our recycled water from. The purple area is our proposed site, and then the inside gray box is our proposed building, which my teammate will get to eventually. Some key things to note here. Obviously, our main design, I would say, was the domestic water line going from our treatment facility to the existing water line on La Paz Road. I have obviously all the existing utilities in the area, so sewer, storm drain, recycled water. Kind of hard to see, you'll see on the next slide, but I have the domestic water in there as well. And then to the north of our site is the Laguna Niguel Regional Park. First thing for our design was coming up with our pipeline alternatives for our pipeline routing. You can see on the left side, we have our three main alternatives that we came up with. They all had strengths, weaknesses. We ended up with this finalized pipeline routing, which goes along the access plant road. And this ended up being the best option, just so we didn't disturb wildlife, the park area, based on other easements and properties. One major design difficulty, I would say, is that there is a bridge that goes over Sulphur Creek, and so figuring out how we wanted to route the pipeline over that, which was interesting, and you'll see on the next slide. And obviously connecting to the existing line on La Paz, we just used T. Alright, so now we're getting into it. This slide is the first slide for the domestic water line going from our site, which you can see in purple, going up the access road. Something major to note here is you can see kind of in the middle of the profile view with the cross hatching, that is the bridge. So we decided to have that section of the pipe exposed, which means you need to use a different type of piping, which is the ductile iron piping per MNWD and OCPW standards. So for all underground lines, it's C900 PVC, and then for the above ground is the ductile iron. The other area that is exposed is just at the point of connection to our site, just to go based on where our pump is going out before going underground. But for this section, most of it is underground. It runs along the treatment train. Yeah, okay. And then continuing on, you can see going up to La Paz, same sort of deal. This stretch is all underground, so using the C900 pipe, which I did forget to mention, but it is 12-inch. Nothing much different here. Connecting with a T, we're connecting on La Paz to a 16-inch ductile iron pipe, which is roughly 8 feet underground. So you can see on the profile on the far left, that's what I was making as my point of connection. The next off-site section of improvement was going from the existing RTP facility to our facility. And for this is a design pipeline we came up with. It's also going to be C900 12-inch pipe, and then 12-inch ductile iron for the part of the pipe that is out of the ground, which for most of this pipeline, we decided to try to have it be gravity fed to reduce the amount of pumping and cost needed. So most of this pipe is actually out of the ground because where the plant access road is, it goes off the side slope and there's a drainage ditch. So initially I was gonna have to maybe go over that, and based on the elevation, I kept the whole thing out of the ground. And the last part of our offsite improvement is the park area. So you can see the blue line, that is what Black and Beach gave us as our proposed property line. But we kind of wanted to preserve the park as much as possible and not eat into it if we could try. And you can see inside that blue area is a existing bathroom, some trailheads, a walkway to an amphitheater. So we wanted to preserve that. Obviously, to put our site in, we did have to take about 50 parking spots away. So that was something we had to think through. And so you can see along the road, the darker parking spots, those are spots we were able to add in. So we added about 19, so we got about half the spots, which I think is better than nothing. And then I had to add a cul-de-sac, which is per the OCPW standards. And the only other improvement to the park is just in the far left of your screen on the bottom. There's a small section of the trail that had to be rerouted due to our site project boundary. And so now I will hand it off to Ford to talk about the onsite.
Thank you, Matthew, for that eloquently presented section of the presentation for offsite aspects. I'll now discuss many aspects of the onsite exterior layout, as you can see on your screen, which correspond to the purple area of this drawing, and also the light blue pentagonal project boundary in the drawing you see on both our drawings. The project line is cropped to on the right-hand side. I collaborated very closely with them through an iterative design process, where activities such as lining influent and effluent pipelines and facilities, etc. were done. I also worked to add an additional cul-de-sac with 6 additional parking spots on the southeastern entrance of the facility, similar to what was added on the northeastern entrance, and ensured that the pedestrian pathway was appropriately routed around the building. As Matthew and I both made an environmental effort to preserve as much of the existing parking as possible, as he just mentioned, when designing both on-site and off-site components of the facility. Next, I'd like to direct your attention to the on-site interior layout of the facility, where I was in charge of taking measurements of each treatment train component from my teammates' research and attempting to find an appropriate size and layout of the facility building to fit all the components into it, while also allowing it to fit within the defined project boundary, or the light blue pentagonal line that you just saw. In order to fit all the treatment train components in, the final design of the facility has 2 floors, where the first floor is on the left and the second floor is on the right. The dimensions are 227 feet by 250 feet in length and width dimension respectively, and the height of the facility is 25 feet tall for the first floor and 15 feet tall for the second floor. The measurements were taken from the tallest component, plus a 5-foot buffer from each floor, which in this case was the ESB with an engineered storage buffer tank on the first floor at 20 feet, and the chlorination tanks for the second floor at 10 feet. You also notice in the design that we chose 2 parallel treatment trains at 1.5 mgd each for redundancy, for a total of 3 mgd. Now I'll walk you through how water will flow throughout the facility. It will first flow through the ESB on the first floor, where it is pumped. Can't kind of see it, but will first flow through the ESB on the first floor, where it is pumped to the ozone and the BAC process, also on the first floor, before being pumped to the second floor, where it goes through the membrane, RO, UV, and chlorination tanks, before flowing down into the post-treatment storage, before being pumped out with 2 pumps in series in the same building to ensure sufficient head to the point of connection at La Paz Road. For the chemicals used in the facility, I added liquid oxygen storage areas with the reduction of ozone on the first floor, while citric acid and sodium hydroxide, also known as caustic storage, for the membrane, pretreatment, anti-scalants, and sulfuric acid storage for the RO, oxidant storage for the UV, and chlorine storage areas are all on the second floor. Lastly, I'll talk about miscellaneous items in the facility that I added for ease of maintenance. The blue color are platforms and steps, so engineers conducting maintenance can walk over the pipes and transport chemicals to various areas of the facility. While we also have 2 freight elevators to transport items between the floors, stairs in the top left, center, and bottom right of the facility in the drawing, and 2 maintenance hatches in the second floor above the northeastern entrance, so components too large to fit in the elevator can be pulled out with a crane at the side of the building. The SCADA control room and electrical room and plus emergency generators are all on the first floor as well. Thank you.
Hi, I'll be speaking about our pump selection. So upon some research, I've decided to choose the Grundfos LS 350-300 pump purely based on its suction and discharge flange sizes, which is 350 to 300 millimeters. And that I chose that because it corresponds well with my teammate Matt's pipeline routing pipe diameter, which is 12 inches. But essentially, a little bit about the specifics of this pump is that its rated power is about But essentially these pumps will run in series, transporting our water from our facility to an existing water main. And the total dynamic head at which that happens would be about 54.43 feet. And that includes the elevation head, friction loss, minor loss, and the velocity head. Thank you.
So now Christina and I will talk about the estimated project costs. So as you see in the middle of your screen there, we have a total estimated cost of $125 million for the project. This accounts for everything involved with the project. So we have our products and materials, the actual facility itself, but we also and that also encompasses the treatment train components. And then we also have the construction, labor costs, as well as design costs and permitting. And then on top of all those costs, we added the 20% contingency cost to account for extra costs and inflation. So further breaking down this project cost, you can see that our products and materials, again, which accounts for treatment train components, it accounts for our pumps, piping, tanks. It also has freight elevators and emergency generators and the facility structure itself. All this accounts for about $36 million in the project. And then diving into the construction, labor, and design, we have the construction itself. So every step of the way, you have your earthwork, laying out the foundation of the facility itself, actually constructing the facility, and then bringing in all of your components. So hauling in all of your components, piping, valves, everything involved with the facility, and then you have your laboring. So your union workers who are there for every step of the way. That accounts for a big part of the cost. And then finally, you have your engineering design consulting work. So all of the engineers involved with the entire design project. So you have your surveyors, soil testers, beginning all the way until your hydraulic engineers, wastewater engineers who are helping out to just design the facility itself. You also have structural engineers, geotechnical engineers. All these different engineers are accounting for some part of the design, and so that those costs are accumulate to about $55 million. And Christina will talk about permitting costs.
So for the estimated total permitting cost will be around $12 million. This includes federal and local and even water rights permits, and even outreach legal fees, which is needed to be approved and basically checked and marked in order that the project will be possible. Note that the permitting application process requires a engineering report, joint plans, and technical engineering, financial capacity, and making sure that it's financially well established and make sure it operates every time, and also to make sure that it's always monitored at all times.
And then one of our last slides here, just a fun little slide showing the fact that we got the Dean's Choice Award last quarter, which was pretty exciting for us. I think the fact that we, got our message across about how important this kind of project is for California and Southern California, I think that really engaged our listeners